Great. Welcome, everyone, to the first Zoominar of the year. Zoominar on the topic of modulational instability. We're really delighted to have two speakers with us. Before that, two announcements to make. We have two members of the committee leaving. Nick Pizzo and Jessica Meixner have left the committee, so we'd like to thank them for their contributions over the past 2 years. We have two new members. We have Xingchang Liu, who's here with us. Maybe you wave at, yeah. So really great to have him on the team. And we have Bernard Akawaze. I can't see Bernard, but if Bernard is there, please do wave at the rest of us. So these are two new members. They'll be chairing this year. And also, if you are interested in speaking, but not quite sure whether the topic would fit, you can approach them individually. But also you can email the Zoominar address if you'd like to speak this year. We're presently in the process of putting together the program for the next year, and there are still vacancies. So you have ideas of speakers who should speak, or you would like to speak yourself across the whole range of academic ranks, from PhD candidates all the way to full professors. We'd like to really welcome all their contributions. With that, I'd like to kick off today. We have two speakers on modulational instability. Our first speaker is Raphael Stuhlmeier from the University of Plymouth. Raphael, I'm going to stop my screen share and let you take over.
All right, thank you very much. Let me just start my screen sharing. So is that visible to everybody?
Yeah, very clear.
Okay, wonderful. So, thank you again for the opportunity to speak at this WISE Zoominar. So it's a real pleasure to be giving this talk. Now, I apologize for the really long and kind of unwieldy title. I wanted to put all of the interesting, well, most of the interesting things that I think are in this talk in the title to advertise it. Hopefully it hasn't scared people away. I'd also like to acknowledge my co-author, David Andrade, who's now at University of Rosario in Bogota, with whom this work was performed. So before I get started, a little bit about the background of this work for me. So actually, although I'm going to be talking about something deterministic, actually I started to try to ask myself the questions that I'll be answering in some sense while working on stochastic wave modeling, in particular when looking at the instability of wave spectra. So we know that wave spectra, of course, they're derived under assumptions of homogeneity. And then there's some work by Albert in the late 70s. Albert and Safman did the work, and then it was taken up by Crawford and coworkers at TRW a little bit later, looking at whether a spectrum is stable or unstable to inhomogeneous disturbances. And so Albert, I don't want to get into the details, but effectively he finds a kind of instability criteria. I've highlighted the abstract right here, which corresponds to a kind of Benjamin Fair instability in the stochastic setting. But the thing that was always missing for me in investigating this work, because this is all in deep water, is where is the inhomogeneity coming from? So in order to have instability of a homogeneous spectrum, you need to add some inhomogeneity. And there's a kind of lore or things that people say, well, nonlinear interaction leads to phase coherence, and so departures from homogeneity. And I couldn't really find a good, simple example where you could appreciate how that works. And so I spent some time with some detours and so on trying to find that example. And what I landed on is Benjamin Fair instability, because it's fairly simple. And I think you can understand a lot. I understood a lot, and I learned a lot by looking at this instability. And the Benjamin Fair instability, so it's here in these two very, very famous pictures in, let's say, fluid mechanics or water waves from the last century, is, of course, the disintegration of wave trains on the surface of deep water. And it's a process of energy exchange that you can also see in Fourier space. So here, these are Flume experiments. So we're looking at Fourier space in F. And I've got a kind of a almost monochromatic wave with some noise. And I mean, I think everybody here will be familiar with the process. Unfortunately, what happens is that that noise, namely these sidebands, so equally spaced Fourier modes, are amplified in a kind of energy exchange mechanism. And this energy exchange, it happens to be something that comes in at cubic nonlinearity in the water wave equations. So this is the kind of the physical scenario. It's what you would measure in a wave flume and how you would see it maybe in those two previous pictures. How do you model it mathematically? Well, you need some equations of motion, and you could do a variety of things. You could start with NLS, or you could start with modifications thereof. I'm going to start actually with the discretized version of the Zakharov equation. And so this equation is, and it comes from exactly Zakharov's paper with a few modifications by Krasicki to the kernel functions in 1994. So this is posed in terms of complex amplitudes BIs, and I'm writing everything in the discrete formulation. So instead of three integrals, I've got a sum here, and I've got a linear term in the equation of motion, and then I've got these cubically nonlinear term where all of the nasty stuff is really in this kernel. So that's where the physics is encapsulated. I don't want to spend a huge amount of time working or talking through the Zakharov equation. It looks a little bit imposing when you see it initially, but actually, because the complex amplitudes are effectively Fourier amplitudes, it's not so terrible to go back to the free surface. In fact, I think it tends to be pretty straightforward. And I'll give the simplest example of how that works right here. If we have a single mode in the sea, I've got an ODE here in terms of a complex magnitude B. And if I solve that and then basically go back to physical space, I find the Stokes wave, right as Stokes wrote it in 1847, with this frequency correction of order epsilon squared. So it's a third order Stokes theory. And the thing that's missing, of course, are the bound modes. So you might have been looking for them. The bound modes are thrown out because they're non-resonant, so they don't play a role in this description. And to make the connections between this Zakharov approach and maybe more familiar things even more explicit, I'll also say, if you're in the continuous Zakharov case, and you take a narrow band limit, so you're assuming all of your wave numbers are around a carrier wave number, say K0, and you approximate those kernels, because that's how you derive the NLS, and that was what was done by Zakharov in this very, very famous groundbreaking paper in 68. So, okay, these are the equations that I'll start with. Now, what do they have to do with Benjamin Fair instability? The instability arises from a case of a degenerate quartet. So we're at cubic nonlinearity. That means we're looking at interactions of 4 waves. And the very simplest case is if I count one of those waves twice. That's going to be the carrier, so the kind of monochromatic wave that we want to generate. And then B and C are going to be the 2 sidebands. And I can write down a system of equations for those, for this degenerate quartet. It's effectively, it looks like the ODE for the Stokes waves, but now I've got coupled ODEs for A, B, and C for the 3 Fourier modes that occur. So I've got 3 complex ODEs. Okay, where does the instability come out here? I mean, you could solve this system numerically with various initial conditions, but how do you appreciate what the instability looks like? Well, you do the very classical thing. It's due to Crawford and coworkers in this specific context, and is you linearize. So if you've got say a physical case where you're generating a monochromatic or nearly monochromatic wave with a wave maker, your carrier wave Ka is big. And all of the other modes are initially small. It's those things that might grow if you happen to be in an unstable regime. So you linearize assuming that you've got large carrier and small sidebands. And then what you see is that the equation for the carrier actually decouples. So you get a single equation for BA. That's just the equation we saw on the last slide for Stokes waves. So you can solve that. That's Stokes' third order theory right there. Solve it for BA. What you then get is a linear system for BB and BC, and then the eigenvalues of that linear system give you growth for a specific criterion that involves some detuning of the frequencies, and it involves the kernels in some way. And if you take all of the limits that you need to go from the Zakharov system to NLS, well, you'll recover a growth rate that maybe looks familiar for people that have worked in NLS. So if P is the distance between the sidebands and my carrier, so P is sideband separation, epsilon is steepness, Ka is carrier wave number, then you've got this 2√2 threshold for NLS. So the stability diagram in the narrowband case, where I've got sideband separation P on the horizontal and I've got carrier steepness epsilon on the vertical, just looks like this, right? So NLS says everything in the gray area is unstable. And then the Zakharov equation modifies that and tells you, in fact, if you use the full kernels, the full expressions, you find that the stability region is not unbounded, as NLS would predict, but it's bounded. There's a kind of restabilization of very long waves that I'll talk about very briefly. There's also a general restabilization of all waves here. And so there's this kind of horn-shaped region that's been known since the work of Crawford and co-workers. So some natural questions, of course, occur. One is this linearization any good? And then the next one, because I'm assuming small amplitudes, is after the initial growth, right? So the linearization breaks down. So what can you expect? How can you say something about what's going to happen to this system afterwards? And this is, I think, where you can use a little bit of creative rewriting to find a very, very nice, very clear description of the system. And so the first thing I'm going to do is going to introduce the conserved quantities of the cubic Hamiltonian, the conserved quantities of the cubic Zakharov equation, namely momentum in this form here, wave action, looks like this, and then the Hamiltonian itself, or the energy of the system in these variables. And I've done something that's maybe a little bit unusual. So I've written the energy instead of in terms of the complex amplitudes and their conjugates as you would normally do it. I've written the Hamiltonian in terms of action angle variables. And actually, I think this is one of the key steps to seeing how especially the phases play a role in this energy exchange process. So you've got quadratic terms in the Hamiltonian. Those are the linear contributions in the equation of motion. You've got some of these quartic terms here, which again, you see there's no phases here. No phis play a role at all. And these are all of the trivial interactions between waves that don't resonate, but only cause, well, so they resonate, but they don't cause energy exchange. They only cause frequency corrections. So all of these symmetric kernels and symmetric resonances. And then finally, you've got all of the non-trivial resonances that are kind of here, where I've got to fulfill in a non-trivial way this delta function that Ki plus Kj is Kk plus Kl. And that's the only place that the phases actually come into the problem. And they only come into the problem in a specific combination. And that combination is exactly the same as the resonance condition. So this dynamic phase variable really comes out of the Hamiltonian formulation if you rewrite it in terms of action angle variables. And I think identifying that is already about 50% of the work towards reducing Benjamin Fair to what I'm going to show you. So I introduce what I'll call a dynamic phase variable for the degenerate quartet. So counting wave A twice and then taking off the sidebands phi B and phi C. So those are it's the dynamic phase difference in this resonant combination. And then if I stare at the conservation of wave action a little bit, so here it is, I divide through by A, which is a constant for the system, and I identify, let's say, the fraction of the wave action that's in wave A, so that's in the carrier with a new variable eta. It turns out, by essentially simple linear algebra, that you can rewrite the system of 3 complex differential equations, so effectively 6 real equations, in terms of 2 variables. So that variable eta, which is like an energy exchange variable between the carrier and the sidebands, and the variable theta, which is like a phase variable or dynamic phase variable that tells you what is my degenerate quartet doing in phase. Moreover, this dynamical system is itself Hamiltonian. So you can take the reduced Hamiltonian formulation of Zakharov, you can reduce it to these three modes, and then you can introduce this change of variables, and you get a Hamiltonian. So what you've got is, from 6 equations, you're down to a planar Hamiltonian system, which lives on a phase space that has this form, namely a phase space which is a truncated cylinder. I'll show you in a minute where this phase space comes from. But eta, the energy exchange, goes effectively from 0 to 1. And theta, the dynamic phase, goes from minus pi to pi, and it's 2 pi periodic. So what does the phase space look like? Well, I've drawn a typical phase portrait right here for you. And it takes a little bit of time to interpret this. So the first time you see it, you think it's hard to say how this connects to water waves. But if I look at the phase space, here at the top, where eta equals 1, recall the definition of eta. So this is just conservation of wave action. If eta equals 1, that means I don't have any of the sidebands. So those are both 0. So all I've got, the entirety of the wave action, is in my carrier A. So I'm sitting here at the monochromatic wave solutions. These are Stokes waves. So single Fourier mode, the free surface looks like this. At the bottom of the phase space, where eta equals 0, well, I don't have any of mode A, so I don't have any of the carrier. I've only got the sidebands. And then the question is, are the sidebands initially of the same amplitude or not? Because of my conservation laws, if you have initially equal sideband amplitudes, they remain equal for all times. And in fact, then this bottom of the phase space becomes exactly the bichromatic wave. So where the top of the phase space is the Stokes wave solution to the Zakharov equation, the bottom of the phase space is the bichromatic solution, effectively the same as that derived by Longet-Higgins and Phillips in 1962. So I've got two Fourier modes, and they're only undergoing mutual frequency correction due to the cubically nonlinear interaction. In the middle of the phase space, most of my trajectories are going to be periodic things like this. And if you've integrated, say, the Zakharov equation or any similar resonant interaction system, you'll immediately know these plots on the left. So if I start here at this red dot and I go along one of these trajectories, we see that I've got energy exchange where as eta falls, I'm giving energy from the carrier to the sidebands. So right along here, the sidebands grow, and then this process repeats exactly periodically. So there's Poincaré recurrence in this dynamical system. So most of the trajectories that I've got here are these kinds of periodic orbits. There are also a few other points that is worth remarking upon. The dynamical system also has fixed points, and they come out really just from looking at the two equations that we've got. And if you start at one of these fixed points, well, there's no energy exchange. So these are degenerate quartets that are in near resonance, so they fulfill all of my near resonance conditions, but they're at steady state. And in fact, it's interesting to see that a few years before we did this work, there was quite a lot of interest in these steady state resonant and near resonant waves. People found them experimentally, so particularly I'd say the group of Shizhen Liao and in Shanghai Jiaotong. They found them theoretically using this quite complicated numerical methodology. And there's still work on these nowadays. But typically, while the methods are a little bit different, when people have looked for steady state resonant or nearly resonant waves, they've looked for them in isolation. Whereas here, in this dynamical systems viewpoint, you see that these steady states actually exist as a part of the organizing dynamics of this resonant interaction. So once you've got a dynamical system, the other nice thing is that you've reduced, let's say, the number of parameters by a lot. And there are really only two parameters that remain in the problem. One is the total energy or total wave action, and the other is the sideband separation. So what I'm doing in the following animation, which I'll show you, is to fix my carrier wave steepness. That fixes the wave action. And I'll show you how my dynamical system bifurcates with the sideband separation. So here there's a little schematic that shows you where the sidebands are located, and P is sideband separation distance. So if you play the video, you see immediately at P equals 0, there's a bifurcation here where fixed points appear at the top of the phase plane. Remember, the top are Stokes waves, bottom are monochromatic. As sideband separation grows, the bottom fixed points disappear, and then the top fixed points start to come closer and closer together. In fact, as the sideband separation gets further and further apart, we see the top fixed points are starting to approach one another. In a minute, they're going to coalesce and disappear. And then after that, all of the trajectories in phase space basically start to flatten out. So I'm losing energy exchange because you remember in the vertical direction here, as we go in the vertical, that means energy exchange between carrier and sidebands. So what does this have to do with instability? Well, let's look at the instability diagram, the classical one from the Zakharov situation. So the Zakharov system says unstable waves for a given epsilon, let's say epsilon 0.1, need to be in this gray shaded region. These are the unstable monochromatic waves. Those waves live here at the top. So what we're really looking at in Benjamin Fair instability in this setting is the orbital stability of the nullcline that forms the top of this phase space. And I see that as soon as P is larger than 0, fixed points appear, and an orbit that wants to go around the top, if I perturb the top a little bit, needs to go around that separatrix, that black line. It can't cross the separatrix. So it needs to go around, and that itself, that is the orbital stability or instability. As I increase P, and here we see as P gets beyond about 0.25, I exit the instability region, and then effectively the fixed points disappear. So the top stabilizes because then I get orbital stability of these Stokes waves. There's something I mentioned, or I'll mention as well, is that stabilization doesn't mean there's no energy exchange, right? From the linear picture, you might think, okay, if I'm outside of the stability region, there's actually no energy transfer. There is in the full nonlinear system. So if you integrate in such a case along a trajectory like this, you still get some wobbling up and down. It's not, it's not as dramatic as it might be in an unstable case, let's say over here. Now, I want to say a few words about the Zakharov formulation and also about the work of the next speaker, Andrey Gelash, because I think a lot of people don't work with the Zakharov formulation because the kernels are quite imposing. And I'd like to say, if you're interested in using this and you're in deep water and unidirectional, the kernels are really, really easy. In particular, for the degenerate quartet kernel, work of Kachulin et al. In 2019 gives you this expression, which really allows for exact analytical algebraic work. And so there's some fun things that you can do with that. Let's say in our case, because you're looking for fixed points to determine stability, you get fixed points analytically. And some old results that go back to really the 1980s, like the restabilization of those long waves, if you know that that restabilization is caused by the appearance of fixed points, and you've got compact formulas for the kernels that allow you to simplify, you can actually give exact formulas. So this, numerically, people have known that this is around 0.4, 0.41. In fact, restabilization in the Zakharov equation happens for epsilon 1 over root 6. And the entire restabilization is for root 2 minus root 2. So I've got, I think, about 2 minutes left. And I'll just say something about some of the other solutions that you get out of this formulation. So in addition to the periodic orbits and the fixed points, there are also separatrices themselves. And the separatrices are trajectories that asymptotically connect one fixed point, let's say a monochromatic wave here on the top, with another monochromatic wave. So that trajectory is one that turns a monochromatic wave that you see here, so this is the free surface, through a modulated plane wave, which is a three-wave solution, that's the middle panel right here, back to a monochromatic wave. So this is an exact discrete analog of an Akhmediev type breather. Here in the top, you see the envelope of the free surface, showing you this modulation. right? Now, of course, the same kind of thing can happen, albeit for different values of mode separation, if you start with a bichromatic wave. So you've actually got solutions that will connect your bichromatic case to another bichromatic case asymptotically. And there's also another more special case, which I'll talk about in the following context. I promise I'm going to end soon, which is to say fastest growth doesn't imply largest or most growth. So this is the instability region that you've already seen before. And I'll just draw the curve of largest linear growth rate. So this is that kind of classical thing that you would see going back to Crawford et al. Now, this curve where you've got the largest growth rate contrasts, except for a single point, with the curve where you've got the largest energy transfer. And that largest energy transfer is actually full asymptotic conversion. So along the curve here, this red curve, what you've got are a kind of special discrete breather solution, which allows you to convert a monochromatic wave into a bichromatic wave, where the dynamic phase itself remains completely stationary, or vice versa, you can go from bichromatic to monochromatic, and you can see how that looks in the envelope or in the free surface right here. So with that, I think I should sum up. I think this approach provides a really simple but unified description of resonant wave-wave interactions, both for Benjamin Fair and also for other cases. You don't, because you're using the Zakharov equation, have restrictions in bandwidth or unidirectionality. So you can throw in wave numbers, just have two bifurcation parameters. You can identify periodic orbits and the role of phase coherence in the energy transfer, and also get some new explicit solutions and clarify the role of these steady state resonant and near resonant waves, which have been found in recent years. So with that, I think I'll end, and thank you very much for your attention.
Thank you, Raphael. That's really nice. Thank you. We have a couple of minutes. So normally there'd be a loud applause. We don't always have that online, but it's still there in our minds. So we have some time for some questions. So if you do have a question, you can simply speak up. I think we have a question there. You can type them in the chat. Paolo, do you want to go ahead? No, Paolo is raising his hand, which I can't hear you yet, Paolo. Paolo, is it possible your microphone is off? What you can do, Paolo, I can't hear you. You can type it. You want to type it in the chat, or you're not muted. We can see you, so it appears to be a camera setting. Why don't we see if there's another question, and then Paolo might come back. Oh, is he there? No, he's not. Any other questions? Paolo will come back to you in a moment. Do we have any other questions? Yeah, we have a question from Andrey. Andrey, please.
Yes, Raphael, could you please comment on the exact breather solution to Zakharov equation? So, because I was surprised. So you mean like really new exact solution, like similar to Akhmediev breather, but for Zakharov equation?
Okay. What I mean in this case is a solution for the discrete case. Yeah. So if you discretize to a finite number of modes, so in this case 3 modes, you can do it for 4 modes because you've got enough conserved quantities. But after 4 modes, you're well, you need some creativity. But for 3 modes, this is really an exact solution. So it's that separatrix. So I can share the well, okay. So I can share the screen again. So this separatrix is really a solution for the 3 mode Zakharov equation. Yeah. So it's in fact, you can write it down analytically, and all of the computations here are done. So let's say the computations of the free surface or of the envelope are done with the exact analytical formulas for this breather, because you wouldn't necessarily get this from numerical simulation. So if you're looking for this breather via numerics, let's say just trying to solve the system, by using a ODE solver, right? You can solve it via ODE 45 if you like on MATLAB. Actually, numerical noise will destroy this very quickly, because you really need to be exactly on the separatrix. Yeah. But if you're there, this is a solution. Whether you can extend it to more modes, well, is an open question. I think a very interesting question. Yeah.
Okay. See if we if Paolo back, are you able to ask the question? Yes, Paolo, please go ahead.
Okay, thank you. Nice. It's a problem with Linux and Zoom. They don't like each other, actually. Raphael, thank you for the analysis. But what I'm a bit more concerned about the things is that you show a line of time, right? And Crawford equations are, you say they are a linearization of the things. And so when time starts, then they are not valid anymore. So the actual analysis is about a snapshot in time in general, right? This is because I think it creates a bit of confusion in people to see that the things evolve, but they shouldn't evolve in that way. They are only a necessary condition for instability, but the condition for stability is elsewhere. So a stable solution is a stable solution of the linearized system, but the linearized system is not does not derive anymore from the Zakharov equation.
Yes, I agree with what you're saying, but I'll say, so the solutions that I show are it's the full system. It's the three, so I don't linearize anymore. So
yeah, but three equations, but you need to insert once you don't linearize sorry, but the Crawford equations are actually a linearization.
Yes.
Otherwise, you would have an infinite system of equations, right? So another mode should enter the things in the Zakharov equation.
So if in the standard setting, let's say, if I were just to think about the discrete Zakharov equation, right? So with n modes, if I restrict myself to 3 modes only, I get us this system of ODEs. Sorry?
Yeah, but you can't. You can't. With the second wave, you have an infinite cascade of waves.
Yeah.
So you can't restrict. You can restrict only if the amplitudes are small. That's it.
So yes, the
short times.
This is, I think, is probably the critical point here, that how big should n be? Definitely bigger than 3. Yeah. In realistic scenarios, because you're going to get cascading, you're going to get spectral broadening in almost all cases in let's say in real life. But if you're focused only on the triad, so our degenerate quartet, then the 3 equations for the degenerate quartet itself can be solved exactly. And they can be solved exactly, I mean, you can solve them exactly actually via Jacobian elliptic functions in the style of Bretherton and others from the 1960s. My contention is that rather than solving those, then integrating explicitly and then classifying roots of polynomials, which is hard work because of this sensitive parameter dependence, it's actually much more insightful if you can find the correct dynamical variables, like a dynamic phase and energy exchange, then yeah.
I'm trying to look for a natural point. I think that's probably a natural point for me to hand over to the next speaker. And if
yes.
Again, I'm sure we can continue this really nice discussion. Thanks a lot, Raphael, and thanks a lot to the audience for questions. Andrey, if you'd like to share the screen, then we'll get the second talk going. So continuing on similar topic. But,
yes, exactly. So actually, thank
Andrey,
you,
yes,
Raphael. Yes, Raphael a little bit simplified the task for me because he already explained the models, the Zakharov equation. So I was working with Zakharov in Russia, so I was working in this team with Dichenko, Kachulin, and Zakharov. So this work is a kind of continuation of this, which I'm which I'm doing now. And so what I want to present you, it is this paper. It's our recent paper with my colleagues, with Dmitry Kachudin actually, and also students with Sergey Dremov and Rustam Muladjanov. Sergey Dremov is a student, Rustam Muladjanov is my co-author colleague. So maybe it's not easy to explain what we have done in 25 minutes, but I will try. So okay. Okay. So okay. Okay, the work actually is about similar model. So it's a one-dimensional fluid. So I totally understand that for people who work with real ocean waves, it's a kind of toy model, because in this model we don't have any dissipation. We have only one dimension. And we don't have any wave breaking or something like that. So it's a very purified model. But on the other side, it's very interesting from mathematical side, and it's a very fundamental model. And also from experimental point of view, it's interesting because it is possible to perform experiments in water flumes, which really can show the dynamics corresponding to one-dimensional equations. And so the system of equations, it's our flow is potential. That's why we work with Laplace equation for the velocity potential. And this, if we now introduce the boundary conditions for the water surface, we can derive these standard equations at the boundary. So here eta is our water surface elevation. And also we have velocity potential inside of the fluid, and velocity potential psi is the velocity potential at the fluid surface. So y is our surface, and we can actually, it can be shown, it was shown by Zakharov, that the system is Hamiltonian, and these variables eta and psi are canonical variables, which mean that we can rewrite this system, this fundamental system, in the form of Hamiltonian equations. So in this Hamiltonian equation, so this is the Hamiltonian, and this is the canonical variables eta, the surface elevation, and psi, which is the value of velocity potential at the surface. Okay, so in order to solve this system numerically, there is a very powerful technique, which is called RV equation in conformal variables. So in principle, it is possible to solve this system numerically directly in physical space. But for numerical purposes, it's very instructive to do the conformal mapping from this surface to just a flat surface, and find the new variables R and V using our conformal mapping, which can be done numerically. So if you have a kind of Cauchy problem, if you have initial condition, we can always find this conformal transformation from any surface to a flat one. And then the equations which describe the dynamics and nonlinear dynamics of such waves are written here. So they first were noticed by Ovsyannikov like 50 years ago, but then derived more rigorously by Tanvir, and finally in the final form, which we use, they were derived by Dichenko, Kuznetsov, Spektor, and Zakharov in 1996. So these equations can be solved numerically, and then we can come back to physical space. So another approach, which Raphael mentioned, it's Dichenko-Zakharov equations. So how we derive these equations, we need to take the Hamiltonian up to certain order. So this is not exact Hamiltonian anymore. We have now a small parameter, which is our wave steepness. And using this wave steepness parameter, we can expand Hamiltonian, let's say, up to the fourth order. And then in this case, we can derive, then introduce new canonical variables, do one transformation. So this details which I don't want to discuss too much. So we do another canonical transformation from eta and psi to C and C conjugate, and now we obtain the Hamiltonian in this more compact form. And finally, we arrive at the Zakharov-Dichenko equation, so which Raphael mentioned. So, but now they are written in physical space. They're written in physical space, so we don't have this T element here included. So in physical space, it looks like this. And now, again, as Raphael mentioned, if we do the narrow band approximation, we end up with standard NLS equation, just nonlinear Schrödinger equation, which, so both equations describe envelope of the wave field. So if we imagine a kind of water surface, so both C and Q, they describe the water surface, the envelope of the water surface waves. And that's why it's easy to compare actually these two models. So let's say I have the same initial conditions, the same initial condition, and I run it for the Chenkov-Zakharov equation and for NLS equation, and then I can compare which model gives me which result, and which result is. So, for example, we can estimate how far we from exact solution with nonlinear Schrödinger equation model and with the Chenkov-Zakharov model. We can evaluate how good they are by simply comparing C and Q. And to compare them, we just need to do this renormalization, this just rescaling. And then we can just juxtapose them one to one. Okay, so what do we have at the moment? So we have exact equations. We have exact equations which are coming from like earlier equations, and we write them in the form of RV equations in conformal variables. So we have a kind of intermediate model, which is the Chenkov-Zakharov equation. Here we did some approximations about wave steepness, but not too much. And then our like super simplified model is nonlinear Schrödinger equation. Now we have not only wave steepness, small wave steepness, but also narrow band approximation. And this is our the most simple model. But on the other side, this model is completely integrable using inverse scattering transform technique, which is essential for this work. So, and our idea was to compare these three models for such an object as bisoliton. So, and try to track how what difference we can observe for these three models, and also can we use some ideas from integrable nonlinear Schrödinger equation to explain the behavior of bisolitons in all three models. So we have the complete complete procedure how we can relate the different variables. So because we have three different models, one in conformal variables, another one in the variables for water surface elevations, and we have also C variables, and finally we have Q for NLS. We have all the transformation between all of them. We wrote programs which like helps us to compare one-to-one our wave fields. So now, what do we know about? Let's start from NLS equation. So about NLS equation, we know that there is an exact soliton solution. So this is NLS soliton, which we all very well known. And also for the Chenkov-Zakharov equation, there is also exact solution, exact soliton solution. But this solution cannot be written explicitly in analytical form. But this is a solution in what sense? In the sense that if we assume the solution in this form, it's kind of traveling wave with envelope, we can do, this is called Petriashvili method, which converges to a minima, which corresponds to the optimal shape of this C. So which means that because we are in the minima of some process, it means that this object will live forever in this system. So this is really a solution of the system. The only disadvantage that we cannot express it analytically, this shape, but we are sure that this object will not change at infinity. You know, like, so if we consider infinite evolution of this system, we will always have this soliton inside of the system. But for RVE equations, so for exact equations and conformal variables, we don't have such a solution. We don't have such kind of Petriashvili method because the equations are too complicated. So how it looks like? So the single soliton in DZ equation is a well-known object. You can see it here. And if you launch it in simulations of the DZE, as I mentioned, it will live forever. So hundreds, thousands of periods, so it will not change. What about RVE stationary solitons? So the real work of Dychenko and Zakharov, where they try to find an analog of this stationary soliton numerically now for RVE, for exact equations. What we did, because now we don't have Petriashvili method, so what they did, they used soliton of the DZE equation as a kind of guess. They put it to RVE equation, and then they waited some time, and they dumped the radiation which comes out from this soliton. So this soliton starts to radiate because it's not exactly the solution of the RVE equations, and the radiation which comes out of this soliton need to be dumped. It's, for example, here at the end of the computational domain. And after this procedure of kind of purification of the solution, they arrived at this structure, which is a stationary soliton, which leaves thousands of numerical of characteristic periods of this soliton in this system in RVE equations. And that was a kind of big thing at that time, because it can be a sign of integrability of exact equations. So this is actually the very big point in this story, because it's still not known. So nobody knows if the exact equations can be integrable or not. So, but there are some signs, and such signs are these stable solitons in this system. So later there were different works, mostly done by Alexei Slunyaev. He did similar numerical simulations, and also in collaboration with experimental team, he reproduced such solitons numerically in water wave flume. So these objects are like real nonlinear objects which can be seen in experiment. Okay, so and but the main our main object for today is not just a single soliton, it's a bisoliton. So here you see a formula for bisoliton in nonlinear Schrödinger equation. So for NLS, we have analytical solution for two solitons which kind of propagate together and oscillate. So you see here the two snapshots of the modulus of the wave field for this bisoliton, and we have an exact analytical solution for that. So now what happens if we do a similar thing like we did before for RVE equations? So what if we do it for bisolitons? So what if we just put NLS bisoliton into DZE equation and into RVE equation, and then just wait until the radiation disappear, and then so it turned out that actually we can observe a stable bisoliton in DZE, in both DZE and RVE models. So that was observed by Kachulin, Dychenko, and Sergei Dryomov in previous works. So they found that indeed it is possible that such bisolitonic structure can live in both models, and it can live like hundreds and thousands of periods, characteristic time periods. And now our main question is, what are these structures? So, and also, are they exactly periodic or not? Because it's quite difficult to understand it quantitatively, because we can miss some slight changes of the structure shape. So maybe it's not exact solution of the system. So the main question actually, are they exact time periodic solutions of the systems, or they are just extremely long-living objects? So this is the main question. And also, what is the mechanism behind the existence of such structures. So why these two solitons can exist for such a long time in exact hydrodynamical models. And to answer this question, we decided to use the inverse scattering transform for nonlinear Schrödinger equation. So yeah, and what is actually known about time periodic solutions in different nonlinear equations? So integrable models possess multi-soliton time periodic and also quasi-periodic solutions. So example, the nonlinear Schrödinger equation, which you saw, and also, for example, Benjamin-Ohne equation. So in many integrable equations, you can observe time periodic bi and even more solitonic structures. So also in damped and force models, they also have time periodic multi-soliton solutions. So one of the prominent example is Leggiato-Lefebvre model, which is used in optics. So it's basically a nonlinear Schrödinger equation with driving and with dissipation. And in such models, time periodic solutions are also very common. But finding periodic solutions like localized oscillating solitons in other models, it's a kind of big question. So people are working on that. So I can refer to the papers of Wikilink and to the works of the group of Tobias Schneider here at the PFL on Navier-Stokes equations. So people are really trying to find time periodic solutions in different hydrodynamical models, but up to date, I think there is no examples when you have time periodic solution in Hamiltonian system, and when this Hamiltonian system is not integrable. So I think it is not. There is no such examples. Okay. So in our case, our bisolitons, we observe them at moderate steepness, and that's why our idea was to. So because the steepness is moderate, it means that we are quite close to NLS model. And we can try to use the perturbation approach for the NLS model and try to explain the behavior of bisolitons in DZE and in exact model. So this perturbation approach is based on inverse scattering transform. So I will briefly outline what the inverse scattering transform technique is. So essentially, it's an approach to completely integrate the nonlinear Schrödinger equation and other similar models. It is also called nonlinear Fourier transform, and it is based on Lux representation. So there is the fact that this compatibility condition is equivalent to the nonlinear Schrödinger equation itself, and there is an auxiliary scattering problem, which you see here, by solving which you can get the so-called IST portrait. And this IST portrait, you can think of it as a nonlinear analog of Fourier transform of your wave field. So if for linear problems, we have just Fourier harmonics. And now, instead of Fourier harmonics, we have a solution of scattering problem of this for this system of equations. And we have discrete spectrum eigenvalues, and we have continuous spectrum. So the discrete spectrum eigenvalues correspond to solitons in our wave field. And continuous spectrum correspond to kind of nonlinear dispersive waves. So, and if we now turn the linearity down, if we go to weakly nonlinear limit, the solitons disappear, and this continuous spectrum radiation just turns into standard Fourier transform of the wave field. So there is a direct connection to Fourier transform when you go to linear limit. Okay, yes, and there is a one-to-one correspondence between the wave field and IST portrait. Okay, so mathematically, when we what we need to do when we solve the scattering problem, we need to solve the kind of imaginary scattering problem on the potential, like we do in quantum mechanics, and identify the scattering coefficients. And after that, we can get all the information about discrete eigenvalues and the reflection coefficient. So we use our algorithm, which we developed in our group, to efficiently perform this procedure. Okay, so here also a kind of explanation how it is connected, for example, to single soliton solution. So this soliton has different parameters and they are directly connected to discrete eigenvalues. So the amplitude of the soliton is imaginary part of the eigenvalue. The velocity of the soliton is connected to the real part of the eigenvalue. And also we have position and phase parameters which are connected to it's called norming constants of this procedure. So, and the continuous spectrum, the solution from continuous spectrum might look like this. So you see that this is a kind of a non-solitonic object. So it's a non-coherent part, non-coherent object, and it's fully described by reflection coefficient. So this reflection coefficient is, again, it's analog of Fourier transform, but a nonlinear case. So there are also integrals of motion. Here I present 3 of them, but in fact, there are infinite number of integrals of motion for nonlinear Schrödinger equation. And also we have exact and soliton solution because of the integrability. And the particular case I shown you before is a 2 soliton solution. Okay, so one more illustration of how this inverse scattering transform works. Imagine that we have this kind of wave field, and it evolves like this according to nonlinear Schrödinger equation. And we see that here we have a formation of kind of extreme wave, extreme amplitude wave. And because of the formation of this wave, the spectrum broadens, of course. So it broadens with time. But if we look now at inverse scattering transform spectrum, at IST spectrum, the reflection coefficient doesn't change, and the eigenvalues, they also do not change with time. So they behave similarly like Fourier harmonics in linear case. That's why it is called nonlinear Fourier transform. So it's nonlinear analog of Fourier transform, and only phase rotate. Only phase rotates for different parts of the spectrum, like again, like in Fourier transform. So that's why this a very efficient tool to describe nonlinear processes, because we understand that if, for example, it's some initial wave field, we have 2 solitons, which are characterized by 2 certain eigenvalues. Then at the end of the evolution, we will have the same 2 eigenvalues and the same 2 solitons if the evolution is described by NLS. So this approach is very popular. It can be used to characterize different nonlinear processes. There are some examples. So now if you have not exactly NLS model, we can use perturbation approach for the nonlinear Schrödinger equation. So now if we have here right-hand side, then we have well-developed perturbation theory. So, and our idea in our work is to consider DZE equation or RVE equation as NLS, as nonlinear Schrödinger equation, plus some right-hand side. So this is the key idea.
Andrey,
you see,
we can
yes?
try and wrap up in maybe a minute or so, if that.
Yeah, maybe 4 minutes. Is it okay? Yes, because yeah, basically the introduction is very long, but the result is very, very concise. So so this is our main idea. We consider our model as nonlinear Schrödinger equation and right-hand side part, which corresponds to the terms which are included into DZE and RVE model. And here one of the main results. So here you see bisoliton in DZE equation. And this is our eigenvalue analysis of this structure. So you see that we have 2 eigenvalues which correspond to 2 solitons which form this field. And these 2 eigenvalues oscillate. So you see the trajectories of 2 eigenvalues here. And by looking and by analyzing these eigenvalues, we can now quantitatively say that indeed this structure survived during hundreds of time periods, because we look at the eigenvalues and we see that they do not change during the time evolution. So this is the first result. We really shown that this bisoliton in DZE equation is very stable. So, and now the question is how this structure survives. So why actually? We also looked at the continuous spectrum part. So, and we looked at the oscillations, it's like simultaneous oscillations of the total energy, and we found that there is a kind of energy exchange between 3 modes. So this is basically the main result. So we have shown that in terms of IST spectrum, this structure contains 3 key parts. So it contains 2 solitons and continuous spectrum. and there is a constant periodic energy exchange between these three components. So, and this is actually what is interesting. So this is a little bit similar to what Raphael shown you. So Raphael is considering three Fourier harmonics. So instead of Dichenko-Zakharov equation, Raphael considered three harmonics and consider a simplified discrete model. So in this case, it's also a kind of discrete model of Dichenko-Zakharov equation, but in another variables. So actually, in this case, we are not doing any approximation. So there is no approximations. So we just go from this this field to three modes in IST phase space. We have two eigenvalues and continuous spectrum, and we show that there is like exact energy exchange between these three components. Okay, so the main question, which is still remains, what is the role of this tiny radiation here? So you see here that the structure is not exactly just a structure. There is a very, very tiny radiation, and its impact to the energy is less than 1%, but it's still there. So that's why we still have some doubts. We still are not sure that these solutions are really time periodic or not. So because in principle, if this radiation is essential, then it can mean that this structure will disappear maybe after million of oscillation of characteristic time scales, maybe after 10 millions. But nevertheless, in this case, it's not exact solution. But if at some point it would be possible to show that this is really an exact solution, so this, I think, can be a very big thing, and it can be really a sign of integrability. Because similar, so this is result for Dichenko-Zakharov equation, and the similar result we obtained for RVE soliton. So here you see the wave field in real variables, so for real surface elevation. So now it's in kilometers. So you can see how this bi-soliton can live in real physical setup, and we obtained similar result. That the eigenvalues oscillate. Now it's on almost stable trajectories, but these deviations, they can be due to just numerical artifacts of our numerical integration, because for RVE equation it's more tricky to do the integration and also transformation between different variables. So, but basically, yeah, that's it. Yeah, so basically, this is it. So the main result is that we looked at this structure by soliton from the point of view of inverse scattering transform and the perturbation theory approach, and we found that the structure, the mechanism how the structure lives is the energy exchange between three key modes in the IST sense. So it's two soliton eigenvalues and continuous spectrum. And the major question for future is to identify either the structure are exact solutions or not. So the role of this background radiation, and this what we are trying to answer now here at TPFL with in collaboration with the group of Tobias Schneider. So
Thanks
they
a lot,
have.
Andrey. That's wonderful.
Yes.
Yeah.
So thank you very much.
There's a lot of information. I'd like to keep a little bit to the clock. We've eaten into the time for questions a tiny bit, but are there any pressing questions? Of course, first there's a round of applause virtually. Do we have any questions for Andrey that we'd still like to ask? I know some of you are having to leave. Let's see if there are any questions. Maybe we have even a question from our other speaker who has an incisive point, I'm sure.
Oh, well, so sure. So thank you for a very, very interesting talk, Andrey. So I've one very quick question, maybe to start things off. I think when you were looking at the you start off in RVE with some soliton solutions for the NLS, and then you let radiation kind of you let some oscillations radiate off. Is your amplitude? It seemed like the amplitude of the soliton itself wasn't really decreasing so much. Is that the case, or does the soliton decrease in amplitude because of this? Because you're taking energy away?
Yes, the amplitude decreases a bit. I just didn't show it because I didn't show exactly how the initial condition evolves at the end. Because then what I shown, it was evolution after this procedure. So at the end, we switch off the damping. So and at the end, we work just with this pure to solitonic structure. So and so it's starting from some point, we do not observe any other radiation leaving from the structure. And so, but if if you look at the initial condition, of course, you have some energy decrease and the amplitude of soliton decreases. Yeah.
Thank you.
This is just not shown here.
Thank you. I'm going to be a ruthless chair and draw today's Zoominar to a close. Andrey, thank you very much for your talk. Raphael, also thank you very much for your talk. Will be posted online, and for those interested in further details, I'm sure they'll have the contact details as well of Andrey and Raphael. Thanks very much, and I look forward to seeing you about a month from now at the next Zoominar.